Go ahead.
Hello, and thank you so much for inviting us, Cassie. I really appreciate it. I'm Jennifer Terry, and I've spent the last 10 years, I probably know several of the participants, some friendly faces there, working on land and water issues here in the state of Iowa. And I brought with me three folks who are some of my science advisors on the new CISWRA project that we started at the county about a year ago. So I'll let each one of them do a quick intro, and then we'll launch into our presentation.
Hi, I'm Mary Skopek. I'm the science advisor co-lead with Jen Terry. My day job is I work at Iowa Lakeside Laboratory in Northwest Iowa.
Hi, everyone. My name is Elliot Anderson. I'm a postdoc who works at the University of Iowa, and I'm one of the major research support people on the CISWRA project.
I'm Calvin Walter. I retired after 35 years with the DNR as a GIS analyst, and now I'm working part-time for the Iowa Geological Survey in that same kind of position.
So as Elliot gets the presentation queued up, I will just start a little background on CISWRA and the county. Central Iowa Source Water Research Assessment is what CISWRA stands for, and some of you maybe have already heard of it. So a lot of the time people ask me the question, why CISWRA? So why are we doing it, and what is CISWRA? So we'll start off by saying, why CISWRA? So everybody that's involved in this call and beyond these borders probably realize, if you're plugged into the water scene, how important the two rivers, the Des Moines and the Raccoon Rivers, are to Central Iowa and everybody in our state. But from a topic of local economic growth or culture or recreation, and of course as a drinking water source for 600,000 Central Iowans, as well as one of the most popular fishing spots in the whole state of Iowa is at the confluence. And we find that fishing is not only for recreation here in the metro, but it's also for subsistence fishing. So supports household foods and things. So there's a lot of reasons, including the Icon Water Trails project, why the Des Moines and the Raccoon Rivers are so important to the metro. So that's why CISWRA. And then when people ask me, what is CISWRA? I tell them that Polk County already has a history of supporting clean water in the metro and upstream of us. And I know that Rich Leopold's involved in the call. Rich Leopold, John Swanson, Amanda Brown, and others at the county, including the Board of Supervisors, have prioritized clean water as a very important priority of theirs. And so when the American Rescue Plan Act made money available to the county, one of the priorities that they wanted to spend some of that money on, invest in, is clean water. And so one of the projects that they decided to commission was CISWRA. So it's a 2-year water quality improvement project. The whole project is a scientifically based, unbiased study of what's in the Des Moines and the Raccoon Rivers. And if you're like me, over the last decade, I have people ask me all the time, what is in these rivers? Do you think they're safe? Do we even know what's in there? So there have been a lot of people who have done studies of the Des Moines and the Raccoon River. And so we've been using those data sets as well as dozens or hundreds of other data sets, reports, and journal articles to study what's going on in the rivers in terms of microbiology, chemistry, hydrology, and ecological health. So that's why we're doing CISWRA, and that's what CISWRA is. And the group that I brought with me today are 3 of my researchers on the project. So we've already logged over 1,700 hours of research and analysis by the team of researchers that the county recruited for this project. And you can see the list of the folks there. Some of them are familiar names, some of them are likely not. But they've been really digging into data sets from as many sources as we could possibly find. And so today we're here to talk about not recommendations or findings as yet, because the project won't conclude and have a final report until the end of the year, but we wanted to give you a little taste for what we've been studying and what we're finding, because it's really, I think, going to be of interest to lots of people in the metro.
So one of the things we want to highlight is how CISWRA is different from other previous assessments and studies. And as Jen indicated, there's been lots of work done on the Des Moines and Raccoon Rivers. I think the thing that really sets us apart is that we are trying to be as comprehensive as possible. So we've identified all the existing identifiable and available data sets that are out there, and any research publications or studies that are in the gray or white literature really pulling all that together and really reviewing that and looking very carefully at all that information. So we like to say no stone is unturned. If you think there's a data set out there or a study that we haven't seen, we'd love to hear from you. But we're really trying to be as comprehensive as possible. If we think about being comprehensive and having sort of this water quality universe, where we would look at every possible location, if you think about streams and wetlands and groundwater and beaches and lakes and all of that, that would be our water quality universe. And then if we looked at every possible contaminant, whether it's nitrogen or bacteria, PFAS, metals, whatever, that entire universe, typically, if you think about the impaired waters list, which you may have heard about. And last week, the impaired waters list was actually given from the Iowa DNR. There's a series of funnels that kind of walk through developing an impaired waters list. And so to have an impaired waters list, first that stream or lake or wetland has to have a designated use, whether that's swimming, fishing, drinkable water. And then you have to apply a standard to that particular parameter. So for example, bacteria or nitrate. And then you have to have monitoring data to assess the standard for that designated use. And so after you go through a series of funnels, you end up with this final impaired waters list. And in Iowa, we have 236 stream segments in the CISWRA watershed, but the vast majority of those waters are either not assessed, there's not enough information to really do an assessment, and so we're left with a very small slice of what we can say about those waters. So CISWRA is much broader and bigger than the impaired waters list that you've probably heard about. And again, that universe of the quality of the resource includes all those biological, chemical, and physical parameters, things that you may think about, like nitrate that we've talked a little bit already about, but also things that you maybe don't think about. So the hydrology, how much water is in the stream, how fast is that water coming down the stream, things like the temperature of the water or the dissolved oxygen of the water, the fish and the bugs that live in the stream, as well as algae and sediment and all those. So CISWRA is really that comprehensive view of the quality of the resource. The work is ongoing, and so we've started this project about a year ago. And again, as I said, really leaving no stone unturned with all the different data sets from different partners, everything from the U.S. Army Corps of Engineers to the Department of Natural Resources, Department of Agriculture, the Soybean Association, the City of Des Moines, basically everything that we can find in terms of data sources. And we've spent time talking to each of their partners about what information they think that we should be looking at during this project. As I said, we're really looking at this as being actionable science. So we will do a comprehensive final scientific assessment that really looks at the condition of the water quality in the Des Moines and Raccoon Rivers. Upon finishing that assessment, though, we will start to look at recommendations for improving water quality. And these are recommendations that are going to be actionable for the Polk County supervisors, for watershed associations that are out there, for any group that really has got an ability to start to affect change in water quality. We will have an executive summary and key findings. And again, really looking at what kind of recommendations we can formulate from this really important study that we've done over the past year. Today, we will not be talking about any final recommendations and really just showing you a little smattering of the data. Because we're in the middle of doing this assessment, these results are likely to be reviewed and subject to change. So don't hang your head on anything today, but Elliot and Calvin are going to go through some of the information that we've looked at and some sort of preliminary analyses.
Great, thanks, Mary. So as Mary just mentioned, we wanted to dedicate the majority of the rest of this presentation to talking through some of these initial research questions that we've been tackling thus far. You know, as Jen and Mary highlighted, the world of water quality is a very diverse one that touches a whole bunch of aspects, a whole bunch of different aspects of people's lives. And when we talk about water quality, we're concerned with issues related to recreation, issues related to ecological health, issues related to human health and pollutant transport. And so we're going to touch on a couple of those different issues throughout the remainder of our talk today. But before we jump into that, I really just want to stress that while we do have Central Iowa and we are working officially for Polk County, this research project is not solely focused on Polk County. So our data sets that we've been combing over contain data from all of the watershed area above the Des Moines and Raccoon Rivers as they enter Polk County. And so I've got our project area highlighted over here on the right. And so just for visual purposes, I've combined the Raccoon and the Des Moines River watershed to show the areas that we've been collecting data, have been analyzing so far in this project. Of course, we're still interested in the classic water bodies like Saylorville, Beaver Creek, Walnut Creek, the lower portions of the Des Moines and the Raccoon. But I just want to stress that in our analyses, we're not simply focused on those issues, because often, a lot of times, the water quality challenges that we see in local waters are related to different practices or different climate situations that are occurring in the upstream watersheds. So I'll start with an example here of how we've analyzed some of Iowa's historical flow data. So all around the state, the United States Geological Survey operates many different stream flow gauges that constantly measure how much flow is going through our rivers. And what I've done here is isolated the gauges that are within our project area and shown the time frames from which we have available data. The big takeaway here is that flow data is pretty unique in that in many locations, it goes back several decades. And we have instances of flow data extending back to the 1920s and even before that in some places in Iowa. So I'm hoping you guys will recognize a few of the major rivers that we've got within our watershed here. So these are different locations along the main stem of the Des Moines River. We've got the Boone River, several other smaller creeks, and it's a similar situation with the Raccoon River over here on the lower portion of this graph. So one of the unique findings that we've been able to take a look at is how these flow conditions have changed throughout the watershed over the past several decades. We did an analysis beginning in 1940, and the values that I've got shown here on the plots are flow data points collected from just below the confluence of the Des Moines and the Raccoon River. But really, we see similar sorts of patterns no matter where we look throughout the watershed. And so what we've been able to take a look at here and demonstrate is that the flow conditions in these rivers have changed significantly. And there's a general story where these rivers are seeing more flow now than they ever have been before. But as you look at things a little bit closer, there's a bit of a more complicated picture. So in the top left-hand figure that I've got shown here, these are the lowest flows for every single year collected from 1940 to the present. And if you just pull out those low flow days, what you see here is a really, really steep increase in the amount of flow that's been passing through these rivers. If you look at the mean flows from each year, so the annual average flow, which is shown here in the middle graph, we're also seeing an increase, but it's not quite as big. It's not quite as steep as those values related to the low flows. On the top right-hand graphic here, we've got the biggest flows in every single year. So these are the flows that are going to correspond to the flooding conditions that most of us are familiar with. We see a minor increase here, but it's not quite as big or as pronounced as what is occurring in the other two rivers. And so this comes together to tell a story of a changing river flow condition where we have more water in the rivers than there's ever been, but there's more water at these low flow conditions than we've seen historically. So these rivers aren't as prone to drying out. They aren't as prone to having these really, really low flow conditions where there's almost no water available for recreation in some of the larger rivers like the Des Moines or the Raccoon. They're also a little less dynamic, so we don't see the rivers go from really low flow to really high flow conditions as quickly as we used to in previous years. And so this is, it's hard to tell exactly what the cause of this is, but we know it's some mixture of land use change and climate change that's been occurring in Iowa throughout the past several decades. And this is an important concept because the state of river flows affects so many other aspects of water quality that we're concerned about. As I mentioned earlier, the amount of flow that's in a river is directly related to its ecological health. It's directly related to its potential for recreation. These types of flow conditions can tell you a lot about what type of pollutants or contaminants will be entering a water body. So now diving into a couple of specific examples of different pollutants that we've been looking at. So a big one on everyone's mind throughout Iowa throughout these past several years has been nitrate. And so nitrate, we traditionally think about that as a nutrient pollutant that causes a lot of concerns related to drinking water health. And so we have this well-established standard that if the concentration of nitrate in water that you're drinking is above 10 milligrams per liter, that's a problem. That's related to this condition called blue baby syndrome, which some of you may be familiar with. But I just want to mention that we've analyzed this data and looked at it in several of the rivers. And so this is what the Des Moines Water Works treats for. So anytime water is above this 10 milligrams per liter concentration, people over at Des Moines Water Works work hard and make sure it falls beneath this threshold. And so this is the regulatory framework that we have currently existing. But as Mary mentioned, we've been able to take a step beyond that with this CISWRA project and specifically look at this other threshold, which is 5 milligrams per liter. Now, there's been some debate in the scientific community over the past 3 years that this 10 milligram per liter threshold is inadequate. As I just mentioned, it's primarily related to this condition known as blue baby syndrome, but there's increasing evidence that nitrate concentrations at lower levels can also be carcinogenic. They can be cancer causing. And so several federal studies have been initiated trying to get our heads around how much of a problem this is. But within the context of CISWRA, we wanted to do a few analyses to see just how often our rivers are exceeding this 5 milligram per liter threshold. And then finally, there are also some ecological health guidelines concerning nitrate. Since it is a pollutant, if you have, or since it is a nutrient, since you have excess levels in a water body, those can often cause algae to grow out of control, and that has its own set of concerns for ecological health. So here's the result of one of the analyses I was just talking about. This is the number of days going back to the 1970s in a given year which nitrate concentrations in the Raccoon River were above 5 milligrams per liter. And so this is a little bit concerning because we see that this happens a whole bunch. And so we've got nitrate levels that are certainly too high for the ideal ecological health conditions and may have this potential human negative health impacts. And this is something that's been occurring for quite a long time. So, we kind of have this double-edged sword where we have these human health issues and these ecological health issues, and that's what's made nitrate such an important pollutant that's been on a lot of people's minds recently in Iowa. Another factor that we've been looking at, a little bit more related to ecological health and recreational opportunities, is this concept of dissolved oxygen levels. So dissolved oxygen levels within water bodies are important because if the dissolved oxygen levels get too small, then fish, other aquatic life forms that need oxygen to survive, don't have that at their disposal. And so with low dissolved oxygen levels, you can end up in some fish kills, with some fish kills or other negative events. Now, traditionally in Iowa, the thinking has been that we don't struggle with dissolved oxygen levels like we do some of these other pollutants, like nitrate, for example. And that thinking was based off of historically collected data, which looks a lot like the data that I've got shown on the slide here. So these are grab samples taken during the middle of the day, typically when dissolved oxygen levels are the highest at 6 different watersheds throughout our CISWRA project area. And I've got box plots just showing those concentrations. The rule of thumb is if you have dissolved oxygen below 5 milligrams per liter, that's when you have situations that are problematic for aquatic life. I can see from these box plots that it's only a handful of times that dissolved oxygen levels have traditionally gotten that low. And so this was kind of the conventional thinking. But again, with CISWRA, we've been able to take a slightly different look at this data and examine some of these data sets closer and shed a little bit more light on dissolved oxygen levels than we've previously understood. So what I've got shown here in this plot on the left is continuous dissolved oxygen data. So you stick a probe in the water, and so instead of just collecting a sample once a day, or once a month at noon, this is taking measurements every 15 minutes. So you get samples during the day, then you get samples at night. And so what we revealed by looking at these data sets is that we tend to have a lot of high swings in dissolved oxygen. So it can be pretty high during the day, and then at night it can dip down into some levels that are more problematic. And it turns out when you look at dissolved oxygen through this framework, we have some more concerns involving this parameter and aquatic life than we've traditionally been thinking about. When you have those large daily swings in dissolved oxygen, it's generally indicative of an ecosystem that's not very stable, that can cause a lot of algae to bloom and die off all at once. And it's not ideal for other aquatic environments. And so we've delved into data sets like this for the first time, but it just really kind of gets at this larger goal of this project where we're trying to understand areas that people historically haven't investigated so well and bring them to the table and share how they impact all these different areas that we're concerned with regarding water quality. Another item that we've been really digging into a lot lately is this idea of bacterial indicators. And so, as I think most people are aware of, when you have microorganisms in the water, a subset of those are harmful, can be harmful to humans. And so, anytime you get into the water, there's some potential that you could be exposed to one of these bacteria. And so, typically, what we do in this space is we look at a specific subset of bacteria known as E. coli, which is generally viewed as an indicator for the total amount of harmful bacteria that can be in a water body. So, there are a million different microorganisms out there that are potentially harmful for humans. You can't test for them all. So the general thinking is we test for this one, called E. coli, and that's representative of the overall amount of potentially harmful bacteria that exist in a water body. And so this plot here on the left is attempting to show all of the E. coli data that's been collected within our watersheds. I've got things broken down, again, using box plots along a few different dimensions here. So we have E. coli samples broken up into samples that were collected in rivers or streams, samples that were collected on beaches, and samples that were collected in lakes. So not on the beach directly, but farther out into the middle of the water body. And there are a couple of important thresholds that we often talk about when discussing E. coli related to different recreational activities. So we have this 235 threshold. If E. coli values are above that, there's a concerning risk associated with activities like swimming, jumping around in the water, getting your full body submerged. When values exceed this 2880 E. coli level, there's a concern with recreational activities such as paddling, such as more minor exposures where you're not fully in the water, but still making contact with it in one way or another. And so the big takeaway here is that E. coli values can range a whole bunch. And sometimes these rivers are totally fine. There's no bacteria in them at all. But in other times, we have seen data where E. coli values are concerning and are going to pose some sort of negative human health impact. The risk is less when it comes to the beaches, and even less when it comes to the lakes. And so one other way we can summarize this data, if we just look at the values that were collected within the rivers here, is that when you break down these values into those that were collected under different flow conditions, so we have values that were collected, or we have samples that were collected during low flows, samples that were collected during normal flows, and samples that were collected during high flows. No matter which river you look at, we find that during high flows, the water is more likely to be above that 235 E. coli limit. So it's just that there's a little bit there's potential for some E. coli presence in these waters underneath any flow condition, but we can definitively say that as those flows get bigger, there's a higher chance of more E. coli being in the water as well. And now I think Calvin's got a few words to say about some of the more erosion-based work that we've conducted. Take it away, Calvin.
Thank you, Elliot. So obviously Iowa is a very agriculturally intense state, and one of those main characteristics is the fact that we raise a lot of hogs and cattle and chickens and turkeys. And part of our goal is to determine what impact this animal feeding operations have on our water quality, as well as the habitat and effect on the environment. And so we're looking at, here is a map showing a concentration of the animal feeding operations summed up by what we call a hydrologic unit. So there are thousands of these within the state. So we sum up the number of animal units within each of these little watersheds and divide it by the number of crop acres to kind of look at the intensity of animal feeding operations within that watershed. And obviously the higher the number, the more animals manure per acre you're trying to apply. And so we're looking at this amount of manure that may be applied to the landscape, and also what the application methods are, timing around the year when they are being applied, and then perhaps how much is being done within a watershed or a county. And then also looking at not only the nutrients, the nitrogen and phosphorus, but also the potential for other contaminants such as pathogens, antibiotic resistant genes, and then of course the ammonia as well. And then we're going to look at, as Elliot said, looking more at sediment and bank erosion. and turbidity within our streams. And so here's a map showing Walnut Creek over on the west side of Des Moines, coming in from Dallas County. And many of our smaller streams in Iowa were straightened or channelized back in the 1880s to early 1900s, and actually still goes on today, but much to a lesser degree. These straightened channels then have what we call very low sinuosity, which is how much the stream meanders. And you can get a channel that's all the way down to just a value of 1, which means that it's a straight line essentially. And these straight lines are, when you take a channel that's meandering and you straighten it out, you reduce the distance the water has to flow to get from A to B, and that the elevation doesn't change, and so therefore the slope does. And that slope changing increases the velocity of the stream. Go ahead, Elliot. And so these higher stream slopes are directly proportional to the amount of erosive potential that water has. And you can see that these smaller headwater streams are much steeper slope than the main channel, which are typically less than a 0.5% slope, whereas you can get well above 1% slope on these smaller streams. So these smaller streams with the greater slope become deeper and more incised, and then maintain the flow within their channel. So when you have a low, like a small flood, what we would call a 2-year flood, instead of that water getting outside of the channel and dissipating on the floodplain, it continues downstream to the larger streams. And go ahead and next one, Elliot. And also within the urban areas, you end up getting more runoff. So you have this kind of a double-edged sword, like Elliot talked about earlier. You have steeper slope and you get more runoff in an urban area. So the little graph on the right shows that in a rural setting, the one on the left, you only have about 10% of your flow running off into the streams. And over on the far right, you have a suburban setting where about 30% flows off into your streams. But in an urban area, you get 55%. This is not something that we have measured ourselves, but this is something that some other people have measured in urban settings. So with that greater slope, more runoff, these streams that are in the urban settings average 0.4 meters deeper than the small streams that are in the rural or suburban. And this continues on even into the larger streams, which are about 0.3 of a meter deeper. And these deeper channels also create steeper banks, which then have a higher risk of major collapse. And we can see from data that was collected between the late 2000s and 2020, this is 4 Mile Creek, where the confluence of Little 4 Mile Creek comes in. And on the left, you can see there are several very loopy meanders that in the middle picture, those meanders have been cut off due to the high flows. And since we have LIDAR that was collected at about the same time as these photos, we can do a difference calculations between the two LIDAR data sets and show how much bank erosion has occurred between that 10 to 12 year time frame. So that image on the right shows the red being erosion, and the darker the red, the deeper it is. And so those dark reds are like 3 to 4 meters deep that the bank is. And then the light blue is where material has been deposited. So you can see that the width of some of those bank erosion areas is upwards of 25 meters over a 12-year time frame. So we're looking at that bank moving 1 meter per year on average, which is quite a bit. And if you go to the next slide, Elliot, you can see the impact of what happens when that bank is moving and you have the riparian zone with trees that may be falling in. It may be impacting the infrastructure like our roads or people's backyards and houses. So having these straightened first and second order small streams flowing in through an urban setting really creates a problem with our larger streams having their banks trying to contain more water flowing faster, and you get more erosion, which then degrades the habitat because you're having stuff fall in you're having a lot more silt in the stream, which creates embeddedness, which is when the rocks and the cobble and the sand are covered up with this silt, which some fish need for laying their eggs and for macroinvertebrates to live on. And then you also have these hazards for if you want to go kayaking down these streams, you have trees falling in and slump blocks getting in your way, and even creating kind of like little islands in the middle that you might get snagged on. So the whole issue of erosion, which we know is occurring out there, but only now that we have these two LiDAR data sets can we actually go in and show how much is really occurring.
Thank you so much to the three of you. I think it's easy to see why this project is so exciting to me, because just listening to what they had presented today of some preliminary findings, we found things of interest to people who are trying to understand drinking water sources, fishing habitat, recreation and water trails. How pertinent is it that we're talking about erosion, particularly in urban and suburban settings? At the end of the day, when this final scientific assessment, we're going to finish it up at the end of this year, and it's going to be made available to the public in early 2025. I think there's just going to be a broad range of organizations and agencies and water trails folks and watershed management authorities that are going to be able to literally take the key findings of this report, rip out pages, talk to your city planners, talk to your urban planners, talk to your landowners on agricultural ground where to place those conservation practices. Talk to your lawmakers about things. So this is definitely, our vision is not to have this be a report that sits on a shelf. We want it to be useful to all the folks that are on this call today and our partners in the Metro going forward. So the report, when finished, like I said, in early 2025, will be grouped around river and lake recreation, drinking water, ecological health, and river flow. So you've gotten a little taste today for what that report will contain, and we want to make it usable. We want to get your input this year as we continue doing our studying. So if you yourself and your agency or organization know of others that want to get in touch with us, Cassie has our contact information, and mine's also at the end of the presentation. But we'd love to talk with more partners in the Metro just to be sure that we're hitting on all the topics that are challenging or of interest to our partners as we complete our project. So again, thank you for inviting us, Cassie, and thank you for being here today. And if there's any questions, we can stick around for a bit.
Great, thank you guys so much. We do have one question so far. Keep them coming. We've got some time. This is scheduled till 1. So if you'd like to ask the panelists any questions, I will relay them. Just put them in the chat. So the first question is, will the interim GIS data be available prior to the final report?
I guess I'm not sure what interim data he's mentioning or requesting. Most of the GIS data that we've utilized is publicly available data. The one thing that currently, well, it's publicly available, but you would have to do the work with it. But that erosion calculation that I've done was only run so far for Walnut Creek, 4 Mile Creek, and Beaver Creek. But that data has been transferred to Polk County, so they do have that data.
Thank you. Any other questions? Please type them in the chat. I've got one for Jen. How fun / difficult has this been to work with all of these researchers that span, various areas of the Midwest? What have you learned?
Fun / it is fun and challenging. So I run into people all the time who think maybe I'm still at Waterworks. Like, whatever happened to you? I'm like, well, I've been at the county for about a year. This is an awesome project, but it is, as a project manager, we are far flung. Some of us are right here in the Metro. Some are in Maryland or Wisconsin or Chicago. So we get together every month as a group and we talk about our progress and where we are within each one of our teams that we've divided up into. So it's been really rewarding to work with such knowledgeable people who are such seasoned veterans in research, because basically we just unleashed them a year ago and they have such a wide knowledge base and different areas of expertise that it's just been really a joy and a reward to just watch them just unleash on all these different areas. And you've seen that today, just, with what we've shown you today between, Calvin and Elliot and Mary. So it's a project. It's always challenging to get moving forward when people are working remotely, but it's been just super rewarding because I can see in the end it's going to be super useful information. What would you all add to the project as far as your experience?
Well, I think just the interaction. So sometimes these scientists have not worked together. And so again, by coming at it from, an interdisciplinary approach, we've really, I think, seen some really interesting things happen. And that's really valuable to kind of take the science beyond where it's been before. And again, thinking about, we've got people with 30, 40 years of experience, being able to bring that kind of all forward at the same time is really phenomenal.
Yeah, and I think one of the highlights of this project has been, the team that we've got is not just nestled within academia at universities. So I'm with the University of Iowa, and we have people over at Iowa State, but we have several members coming from places like the USGS or Argonne National Laboratories, or Mary's up at Lakeside Labs. And so I think each of us has been able to bring a little bit of a different perspective from our professional backgrounds in our careers to this project, which has been really useful and really essential, just given the wide-ranging nature of the task that's in front of us here.
Right, I agree in that it's been interesting for me in that I've been able to interact with other disciplines within the whole ecological, environmental world. I'm really enjoying working with the fisheries folks at Iowa State and habitat there, and also learning a lot more about bacteria, which I've kind of gotten away from in the last 15 years, but all of it's very interesting.
All right. Thanks, everyone. I don't see any more questions in the chat. So thanks again to our presenters and to everyone that's attended this call today. We will have another Lunch and Learn, virtual Lunch and Learn, scheduled for the end of April. So stay tuned for an email with information on that. If you are not on our WMA email list and you want to be on that list so you can learn about the upcoming Lunch and Learns and other Watershed Management Authority activities, just give me an email and I will add you to our list. So thanks again, everyone, and have a great day.
Thanks, Cassie. Bye-bye.